Eye tracking on the International Space Station. The eye tracking device ETD is a head-mounted device designed for measurement of 3D eye and head movements under experimental and natural conditions. The tracker permits comprehensive measurement of eye movement 3 degrees of freedom and optionally head movement 6 degrees of freedom. It represents a tool for the investigation of sensorimotor behavior, particularly of the vestibular and oculomotor systems in both health and disease. Eye tracking device on ISS. It was originally developed by the German space agency DLR for use on the International Space Station ISS and was uploaded to the station as part of the joint European/Russian space program in early 2000. The device was designed by Prof. Dr. Andrew H. Clark Vestibular Lab, Charite Berlin together with the companies Kronos Vision and Mtronics in Berlin and integrated for space utilization by the Munich-based company Kaiser 3D. In the first set of experiments, conducted by Prof. Clark's team in cooperation with the Moscow Institute for Biomedical Problems, the eye tracking device was used for the measurement of listings. The scientific goal was to determine how listings plane is altered under various gravity conditions. In particular, the influence of long-duration microgravity on board the ISS and of the subsequent return to Earth's gravity was examined. The findings contribute to our understanding of neural plasticity in the vestibular and oculomotor systems. These experiments were commenced in the spring 2004 and continued until late 2008 with a series of cosmonauts and astronauts who each spent 6 months on board the ISS. Operations. Examination of the orientation of listings plane during the course of a prolonged space mission is of particular interest, as on Earth the listings plane appears to be dependent on input from the vestibular system, i.e. detected through the head position with relation to gravity. By exposing the astronaut to the weightlessness of space, this experiment can follow the subsequent adaptation of the astronaut's vestibular system during the flight and after returning to Earth. The key question in this experiment is to what extent the orientation of listings plane is altered by the adaptation of the vestibular system to weightlessness or under gravitational levels less than or greater than those of Earth. A further question is whether the body compensates for the missing inputs from the vestibular system by substituting other mechanisms during long-term spaceflight. Missions. The ETD was employed for this study throughout the period from 2004 to 2008. During each 6-month increment, the experimental procedure was performed at regular 3-week intervals so that the adaptation to microgravity could be evaluated. In addition, equivalent measurements were made over the initial weeks after the return to Earth of each cosmonaut or astronaut. In the meantime, the ETD equipment remains on the ISS as a general-purpose instrument. It is currently in use by a group of Russian scientists from the Institute for Biomedical Problems who are examining eye and head movement coordination in microgravity. Technology. Digital eye tracking cameras designed around state-of-the-art CMOS image sensors are interfaced to a dedicated processor board in the host PC via bidirectional, high-speed digital transmission links 400 Mbit/s. This PCI plug-in board carries the front-end processing architecture, consisting of digital signal processors DSP and programmable logic devices FPGA for binocular, online image, and signal acquisition. For the eye tracking task, a substantial data reduction is performed by the sensor and the front-end processing. Thus, only preselected data are transferred from the imaged sensor through to the host PC, where the final algorithms and data storage are implemented. This eliminates the bottleneck caused by standard frame-by-frame image acquisition, and thus facilitates considerably higher image sampling rates. This processing architecture is integrated into a ruggedized, IBM-compatible PC, which permits visualization of the eyes and the corresponding signals. An important design feature is the digital storage of all image sequences from the cameras as digital files on exchangeable hard disk. After completion of each ISS mission, the hard disk containing the recordings is returned to Earth. This ensures comprehensive and reliable image processing analysis in the investigator's lab and minimizes the time required for the experiment on the ISS. A tracking device on Earth. In parallel to the space-qualified version of the eye tracker, a commercially available model has been manufactured by the company Chronos Vision in Berlin and is installed in many laboratories in Europe, North America, and Asia, where it represents an essential tool for the examination of numerous neurophysiological phenomena.